it. So instead of us spending more time on introduction, just very quickly, my name is Long Zhu. I come from MIT. Okay, and now I'm going to jump start my talk. I hope you can see my mouse. So basically, I'm going to tell you about electron correlation and topology in a material that is known as rhombohedral multilayer graphene. Okay, so my lab at MIT started in 2019, and we're mostly using optical spectroscopy and microscopy technique to study the properties of materials, mainly two-dimensional materials and their heterostructures. And in the recent couple of years, we start to pick up, DC transport measurement at extremely low temperature and a high magnetic field. And that's actually what I'm going to tell you mostly about today. Oops. Okay, before I start, these are the people who contribute to the work I'm going to mention today. My team at MIT and our theorist friends, especially some of the data in the latter part of my talk was actually taken partially in Hong Kong Park's Dealfish here on Harvard campus. Okay, so the topic today is electron correlation. Okay, we know this is a topic that's very old and very fascinating for condensed matter physicists. It happens when electrons are talking with each other. You get this exotic ground states like superconductivity, electron crystals, all these things. And they are very different from phenomena happening in very different material systems. But one common theme they all share is that it happens when the electron energy is dwarfed by some interaction energy, or in another word, when the band of electrons are flat enough. As someone who has been working on two-dimensional materials for my whole career so far, we think this van der Waals coupled 2D material is a nice platform to engineer and study electron correlation. Okay, because there's no chemical bonding between layers, you can assemble this van der Waals heterostructures by choosing the number of layers, the materials to put together, and sometimes give it a twist. Okay, especially recent years, we have seen an explosion of this concept of Moiré superlattice, or someone called Moiré quantum matter, assembled by two-dimensional materials where the two materials adjacent to each other interact with each other, and they have a lattice mismatch or a twist angle or a combination of them, and the result in a periodical potential to modulate the electron states. So the first one was demonstrated by my colleague Pablo at MIT, the so-called magic angle bilayer graphene. And after that, people have been looking at other Moiré superlattice systems, for example, ABC trilayer graphene, HBN, and bilayer transition metal dichalcogenide. Most of the experiment in this field so far have been dominated by electron transport measurement, and many fascinating phenomena have been demonstrated. But in order to have a better understanding of what's going on, we've got to do more than just DC transport, which probes the conductivity at zero frequency, right? We want to do spectroscopy measurement. But apparently, in such materials, it's not as easy to do spectroscopy measurement as could have been done in the more conventional, strongly correlated materials. Here, I just put up a comparison to show some of the aspect to you. For example, the material we are talking about now typically has a lateral size of few microns and a thickness of atomic thickness, okay? And it's much less atoms than a bulk crystal, for example, bisco, that you could study, but you want to extract the same amount of information by performing spectroscopy. As experimentalists, we know that's just hard. And second thing is the energy scale of this Moiré system is so small because the spatial period of Moiré superlattice is way bigger than the atomic lattice scale. As a result, the momentum space and the associated energy scales relevant for the Moiré system is much smaller. And that makes spectroscopy measurement also hard. And third thing is, we can enjoy the benefit of using electrical voltage on the gates to tune properties of these 2D stacks, but at the same time, it's a double blade sword. The existence of the encapsulation layer and the gates layer sometimes could completely dominate the signal that you wish to extract from the layer you actually care about. All these add up makes spectroscopy measurement in such kind of small 2D array system extremely challenging. So part of our effort, as mentioned by Bob previously, you hear or not, was trying to overcome some of the difficulties and still perform reasonable, optical spectroscopy. And this is a work that was published last year. And I just want to briefly mention to you how this works. So the material I'm talking about today is so-called the rhombohedral stacking, okay? Different from the magic angle bilayer graphene, which you have to pick up 2 layers separately and control the angle between them precisely. If you just use Scotch tape to exfoliate graphene and you find a bilayer, it's got to be in the so-called AB stacking, okay? And the difference happens, when you put the 3rd layer on top of it, okay? Bilayer is always AB, but when you choose, put the 3rd layer on top of it, you got to choose to shift either in the left direction, and you get the so-called ABA stacking, or you choose to shift the 3rd layer in the right direction, where you got the so-called ABC stacking or rhombohedral stacking, okay? We're going to focus on rhombohedral stacking because it has some interesting properties. The first of all, intrinsic form of rhombohedral stacking graphene is a 0 band gap semi-metal. It has a band touching point, remains degenerate, because the 2 atoms that contribute to those low energy states come from the very top layer and the very bottom layer. They don't talk to each other directly. So in the pristine form, it has 0 band gap, and the band dispersion is roughly momentum to the cube, because this atom has to go across all the layers before it can reach the other atom. And because these 2 atoms are located at the opposite layer of the stacking order, you can easily break the symmetry between them by applying a vertical electric field using gates, okay? And then you open up the band gap. So you have this additional in situ tunability of the band structure by simply applying gate voltage or electric field. So as we said, the lore we learned from the previous experience of electron correlation in different systems is that we need to get somewhat flat band, okay? And in trilayer graphene, here's how it works. You have a band dispersion that's roughly k to the cube. Well, it's somewhat flat. It's more flat than parabolic band, but probably not flat enough. And here's how you can make it more flat and eventually drive correlation. The first thing you can do is to put it on a moire, okay? HBN and the graphene has a 2% lattice mismatch. Even at 0 degree twisting, there will be a 15 nanometer moire between them. As a result, you've got to fold your original band structure into the mini Brillouin zone defined by the moire superlattice. At the same time, at the boundary of the moire superlattice, the electron state is going to hybridize due to the moire potential and open up a moire gap, okay? So now you squeeze it a little bit and kind of keep it away from the remote states from the second moire band. In addition to that, you can use the other trick by applying an electric field to break the band degeneracy at the 0 energy. If you do that, you'll open up a band gap at the 0 energy. At the same time, due to the band gap, you're squeezing the bandwidth of this moire bands. And then, hopefully, if you open up a big enough gap, you get a flat enough band where electron correlation to start to dominate over the kinetic energy. So this is theory, okay? Experimentally, what we have demonstrated is that, okay, if you really do this procedure and you shine infrared lights, broadband infrared photons onto such materials, and you collect the photocarrier signal to mimic the optical absorption signal, you're going to see some very sharp peak in the spectrum that corresponds to the optical transition from the flat moire valence band to the flat band on the electron side. And that gives you this very big peak. And the second peak you see here in the spectrum, pointed by this green arrow, corresponds to the optical transition from the second moire valence band to the connection band side. While the second band is also somewhat flat in part of it, but overall more dispersive than the first Moray band. So the second peak you see in the spectrum is lower and broader. And the separation between these two peaks roughly tell you how big the Moray potential is. The advantage of this system we're talking about now in the sense of Moray superlattice is it has an additional tuning knob in situ, which is a gate electric field I was talking about, right? When you have small gate electric field, you have a relatively small band gap or low energy of the interband transition. At the same time, the whole spectrum looks dispersive, right? It's not very sharp. But when you crank up your electric field, the peak will blue shift as you're opening up the band gap. At the same time, the peak becomes narrow. So that means you're really driving the system by applying electric field and squeeze the energy range that the electron state can occupy. You're driving the system from where single particle physics dominates to where correlation could dominate. And the narrowest, peak width that you get here is roughly 5 millieV. That tells you roughly how flat the bands we're looking at, okay? This is half of the story. You have somewhat flat band, but how flat is flat? What is the other energy scale? Let's say when you dope charges into the flat band, according to the Hubble model, they are going to repel each other if they locate at the same Moray site. Well, experimentally, what we observed in the half-doped valence band is you kind of lose the track of all those interband transition peaks at high energies, right? They all becomes, somewhat flat. Well, at the low energy, you observe a very big peak that's located at the energy about 18 millieV. That seems to be the only feature that you can identify. So we think this is aligned with a picture that electron correlation split up the valence band into two halves, and you can make optical transition across that gap. And that's what this peak is. If you believe that, this peak position tells you roughly the energy scale of the Coulomb repulsion. And according to our experiment, it's pretty close to a very simple estimate of E squared over Lm, where Lm is the Moray wavelength. So in real space, the picture you should think of is when you have two charges per side corresponding to the half doping of the flat valence band, and your photon get absorbed, and that kick one electron or one hole from its original side to a neighboring side. And by doing that, you have to pay the energy penalty because here, this newcomer is going to be repelled by the two existing charges. At the same time, you save one copy of the Coulomb repulsion from the original side. Overall, you pay the energy penalty that tells you what the on-site Coulomb repulsion is. And remember, the single particle bandwidth we were talking about from the band-to-band transition is on the order of a few millieV at the narrowest, and the Coulomb energy is several times bigger than that. So we think it makes sense to think of the system as something like a mod insulator from the comparison of the two energy scales. So that's what we have done on Moray superlattice between ABC trilayer graphene or rhombohedral trilayer graphene and HBM. At some point, we start to think, okay, Moray is good. It gives you this additional knob to tune things. But how about without Moray at all? Okay, we're dealing with two-dimensional materials, has its in situ tunability, has very high quality. So why don't we think about, how to get electron correlation and topology, even topology, without any Moray, just in the crystal form of 2D materials, okay? And it turns out you don't need to look too far beyond what we have been talking about. We were talking about rhombohedral trilayer graphene, but if you just go a little bit thicker and make it the rhombohedral n-layer graphene, you have a good chance of getting correlation. Basically, this energy dispersion of, proportional to momentum to the layer number is a universal feature of all the rhombohedral stacked multilayer graphene, okay? Think about it, monolayer graphene is energy proportional to momentum, bilayer is parabolic, k squared, and trilayer is roughly to k to the cube, okay? And if you go thicker, the electron from one layer will have to hop more steps before it reaches the other one. As a result, the energy dispersion will become more and more flat. To the zeroth order, the energy dispersion is k to the nth order, and the bigger the n is, the more flat the band will be, okay? Maybe at some point that natural flat band without assistance from Moray or gate electric field is already flat enough to give you something interesting. Of course, you might ask, when will this stop, right? If you extend n to infinite, will this make extremely flat band, well, imperfect, flat band? Well, apparently that doesn't happen because there's other hopping terms you have to include in your calculation. So this are some tight banding calculation of the band dispersion and density states in the rhombohedral series. As you can see, in bilayer, trilayer, in trilayer, you have some saddle point here that give you a Fanful singularity, but the density states corresponding to that singularity is several times, like 5 times smaller than what you can get from n equals 5, for example. Okay, and go from 5 to 6, 7, 8, 9. Well, the density state doesn't seem to really increase much. So maybe we should just look at something like rhombohedral 5-layer graphene, or in the ABC language, 5-layer is called the ABCAB. Okay, so this is from just the flat band point of view. And why do I mention topology? Well, the thing is, the direct point of graphene is kind of some topological object, right? It varies the barrier curvature and the barrier phase. And for monolayer graphene, it has a barrier phase of pi, but for 5-layer graphene, it has a total barrier phase of 5 pi. And that's what happens when you have 0 band gap, right? And once you use a small electric field to break the degeneracy and open up the band gap, well, now all the states near the band gap start to have large barrier curvatures, positive or negative, depending on which value you are looking at, and whether you're applying a positive or negative electric field. So here you got tunable barrier curvatures in this potentially very flat band. And maybe the flat band and the barrier curvature is going to add up and give you something interesting in the topological sense. Okay, and that's the question that we had. And let me show you what we have got so far in this direction. The rest of my talk is all going to be about DC transport at temperatures down to 100 millikelvin so far. So I'm going to show you 2 results. One is about the electron correlation, in this pentalayer rhombohedral graphene or ABCAB graphene. And the other is a Chern insulator state that was observed in the same material. Okay, so since we're talking about DC transport experiment, we make this dual-gated Hall bar device, okay, where the core is a pentalayer graphene and is sandwiched by HBN and dual gate, so we can use top and bottom gate voltage to control both the charge density and the electric field independently. Because it's a Hall bar geometry, we can easily measure the longitudinal and the transverse resistance at the same time precisely. So here is a summary of what we have got, okay? This is about 100 millikelvin, we think. The real electronic temperature could be slightly higher than this, okay? And different from what you expect from a simple doped semiconductor, the phase diagram is actually very rich. If you look at this left panel here, this is a hole doping, while the right-hand side is electron doping, okay? And you see state that's very resistive, that's very red in RXX, and you see state that's very conducting, and you see intermediate state that has shapes that looks funny, right? A ring, a bubble, some boundaries and things. It looks very rich. So let's try to understand what these states correspond to. And first, I would like to focus at where we have electron or holes doped into the system. Okay, let's block this charge neutral state for now. So one thing we can do is to apply a magnetic field that's out of plane, and this will give you quantum oscillations. The degeneracy of the quantum oscillation is, telling you, potentially what is the nature of the ground state, right? Whether some spin or Valley symmetry is broken. For example, in this region here, I'm showing there's a big distance between 2 adjacent features in RXX corresponding to a degeneracy of 4. Well, there are other regions. For example, in this bubble, you see regions that give you a degeneracy of 2, and in some other region, you got a degeneracy of 1. Okay, think about the degeneracy in graphene. You got 2-fold from spin and 2-fold from Valley. So when there's nothing interesting happen, all the 4 species are occupied at the same time equally. You get the so-called full metal. But if some of the degeneracy is broken due to electron correlation, you get the reduced degeneracy. Okay, so we got quarter metal. We got these two are half metal, and this is quarter metal. But this doesn't tell you exactly which degeneracy is broken, right? So in order to differentiate it between different symmetry breaking state, you have to do something else, okay? So based on this, you can tell the degeneracy. But in order to tell whether it's a spin or the valley degeneracy is broken, you've got to do more measurement. So this, involves the measurement of the Hall resistance, okay? In this very, classical paper by Kaplan and Luttinger, they elucidate how this anomalous velocity driven by the barrier curvature can come up in solid states. And if you have barrier curvature, your electron state is going to kind of deflect to the side, and that's going to give you a finite RxY signal to measure. At the same time, if you have barrier curvature, most likely you're also going to have orbital magnetism, because the wave function not only deflect, but also rotate around the center of itself. And that's what we're going to do, okay? In this rhombohedral graphene system, as I show you, at the zero electric field, all the states have zero barrier curvature. But if you apply a small electric field, either positively or negatively, you're going to break the degeneracy and render plus or minus barrier curvature in the states near the band gap, okay? And if you fix the electric field, then you have 4 Fermi surfaces that you could possibly feel, okay? K value spin up, K value spin down, K prime value spin up, K prime value spin down, okay? And the symmetry breaking is all about choosing one of them or multiple of them when the electron correlation happens. For example, if we apply this measurement of RxY to a region where we see the quarter metal degeneracy, we see a jump in the RxY, okay? And the small hysteresis. So this tells us that, 1 out of the 4 isospin copy is occupied, and because that species, that Fermi surface has a finite integral barrier curvature, we have a finite RxY, and that corresponds to the experimental data I'm showing here. Well, in another half metal region, you see, we don't get this jump in RxY. So simply speaking, you can have 2 valleys occupied at the same time and with the same spin. So this is probably corresponding to the Stoner instability, where spin is spontaneous polarized, while the 2 valleys cancel each other. One is blue, the other is red. So you don't get a finite RxY, okay? So if you're familiar with the result that has been obtained from ABC trilayer graphene by Andrew Young's group at UCSB, what we are talking about here is somewhat similar if you only look at the phase diagram at the high doping and the high gated electric field side, okay? They also have quarter metal and spin polarized half metal. But in our case, the purple dot is a quarter metal with spin and valley polarized at the same time, while the yellow dot is also spin polarized half metal. But what's really intriguing for us is what happens here at close to 0 displacement field and 0 charge density. Well, nothing seems to be going on in trilayer graphene. Okay, so basically you got a bubble there. That's what I call it, a bubble. In RxX, it's more resistive than the neighboring state. Okay, neighboring state has about hundreds of ohm in resistance, while this bubble has about 1 order of magnitude bigger resistance. Okay, and if you do the quantum oscillation measurement inside the bubble, there are regions that shows quantum oscillation with a degeneracy of 2. Not everywhere in the bubble. Okay, I have to emphasize that. Not everywhere in the bubble, only in part of the region that has quantum oscillation. And I call those regions wings, just based on the shape. At the same time, I can measure the RxY, the Hall resistance. Okay, as you can see in this wings region, not only I have a degeneracy of 2, I also have pretty big RxY signal. So now I think this states probably correspond to the valley polarized half metal state. Due to the existing flat band in this crystalline pentalar graphene, the band is flat enough to break the isospin symmetry. As a result, you get the valley polarized half metal, which I believe has not been seen in other graphene systems so far. And let's take a closer look at this wings, okay? Here I apply 0.5 Tesla magnetic field. So the color of the region outside the bubble shows you what the normal Hall contribution.
Highly polarized means that the spin is also polarized, or the spin is the same?
It's half metal, so spin, is not involved here.
Half metal.
So two out of the 4 copies, right?
Or yeah, okay.
2 out of the 4 copies. I don't know if the spin locks the value or just completely random. I don't know. All what I can tell is there's a big RXY and it's a half metal.
But it's half though, not quarter.
It's half field, yes. So, so basically in the wings, you see the, big RXY signal, right? And if you do the magnetic hysteresis loop scan, outside the bubble, you don't get hysteresis. Well, inside the bubble, you get hysteresis with varied amplitude of RXY as well as cohesive field. The general trend is when the amplitude of the gate electric field you apply is small, you get small RXY, but you get big cohesive field. Well, if you go to large electric field, your cohesive field shrinks, but the RXY increases roughly in a linear fashion. Okay, so the picture is roughly like this. So when you have small electric field, the orbital magnetization due to the barrier curvature effect is small. So in order to flip it by using magnetic field, you have to overcome the barrier and you have to overcome a big external magnetic field to overcome the barrier. But when the electric field is big, the magnetization themselves, the magnetization is big, so you just need a small magnetic field to flip the orbital magnetization. Okay. One thing to notice is that this, Hall effect seems to be very strong. Okay, this is in a system that has negligible spin-off coupling, it's pure orbital magnetism, and the Hall angle corresponds to a tangent theta of bigger than 0.6. And I'm not an expert on topological materials, but just by doing a simple literature search, it seems this is the biggest Hall angle that you get from any topological metals. Okay, so you have orbital magnetism here, and because we know the microscopic origin of this magnetism is barrier curvature, is an orbital magnetism. We can tell what states these, in the hysteresis loop correspond to. We apply a positive electric field, and at the negative magnetic field, you got K prime with a plus M. And when you apply big electric field, since you fix the electric field, when you apply a big magnetic field, when you switch this orbital magnetization, you go from positive M to negative M. But at the same time, you go from the K prime value to K value, because the 2 values have orbital magnetization at the same electric field. Well, for the negative electric field, on the left-hand side, you get K plus M, and on the right-hand side, you got K prime minus M. Again, magnetic field switch the value and the magnetization at the same time. But the thing is, as you see, on the negative magnetic field side, you actually have 2 states that correspond to the same magnetization, but in opposite value. In the case of sweeping magnetic field, it doesn't matter which value you're in. The magnetic field just choose whichever value that has magnetization aligned with the field. And when the magnetic field is switched, both value and magnetization are switched. Okay. So this is still somewhat the usual magnetic hysteresis you got from magnet, no matter if it's a spin magnet or orbital magnet. What's interesting is that if you scan, instead of the magnetic field, you scan the electric field in this bubble region, okay? This is still the wings kind of rotated 90 degrees. What you find is that you also get hysteresis. From negative to positive, from positive to negative, the color of these wings are reversed. And this is down in external magnetic field of very small, like 20 millitesla or so. So if I do a line cut at the fixed charge density, I got this kind of butterfly-shaped hysteresis. I'm sorry, I'm giving you all these acronyms of bubble, wings, butterfly. I promise this is the last one. Okay, you got this butterfly-shaped hysteresis in RXY. This is kind of bizarre, right? Because this state is, let's say, it's polarized in the K value, and you decrease the electric field, and there's a small magnetic field applied. So when you go through E equals 0, you see in the same value, the magnetization is, the sign is flipped, right? So naturally, you would think the system would just immediately jump to the other valley because now the other valley has the right sign of magnetization to be aligned with the external magnetic field. So the system would do that to lower its energy, but that doesn't happen. It seems the system chooses to stay in the same valley along this blue line, no matter if it carries positive or negative magnetization. And then you get out of the region, the bubble region, and when you come back, it jumps onto the other branch, which corresponds to the K prime valley. So you got this kind of hysteresis that actually corresponds to the valley polarization. When you sweep electric field, this is different from the magnetic hysteresis, because in this case, the magnetization change sign immediately as electric field goes through zero, but the valley polarization doesn't. So you can plot, this butterfly, okay? So I showed you the butterfly obtained with a 20 millitesla outer plane field applied. But if you flip the sign of the magnetic field to make it negative, you also get a butterfly, but this time the butterfly is kind of the opposite of what you got from positive magnetic field. So converting the RxY plots versus electric field to valley polarization. With a positive B, you get this kind of clockwise hysteresis of valley polarization. Well, when you flip the sign of magnetic field, you got the counterclockwise version of the butterfly, okay? So they are the opposite of each other if you plot versus E. But if you plot versus E dot B instead of E or B independently, well, they are unified to both be, winding clockwise. So this tells you that the field that corresponds to this valley order is not E, is not B, is instead E dot B. Okay, the product of E and B choose which valley to you get. So yes, so basically, here we're demonstrating a Ferro-Valleytricity order. The system spontaneously populated one valley over the other one. And that's sort of, interesting because that means if you go along this blue line or the orange line, you stay in the same valley, even if at where your orbital magnetization is zero. When the electric field is zero, you don't have orbital magnetization, you don't have anomalous Hall, but you can still have a valley polarization into, in a Fermi surface where the barrier curvature is just zero. So later we examined how this butterfly evolves, for example, as a function of magnetic field, okay? We just apply bigger and bigger magnetic field, outer plane. As you can see, if you do line cut, this hysteresis loop becomes smaller, right? At the lowest temperature and lowest magnetic field, the butterfly occupies pretty much the whole range of the bubble. But with increasing magnetic field, the butterfly shrinks smaller and smaller. Eventually, it becomes an M shape or a W shape. So this is when the external magnetic field is big enough that you don't need to worry about Ferro-Valleytricity. It's just a minus M dot B term is big enough to determine which state you choose, right? So it evolves into M or W when the butterfly is killed. Another thing you can do is to warm up the sample a little bit, okay? Instead of at temperature of like hundreds of millikelvin, as you increase the temperature, this butterfly also shrinks in the range it occupies, and eventually at about 2 Kelvin, this butterfly is completely gone, and you got the W shape, right? So basically, the whole picture to think about the effect of external magnetic field and temperature is you have two states to choose from, okay? K minus M or K prime plus M. And there's a barrier between them. Applying magnetic field helps you, stabilize one of them and destabilize the other one. At the same time, the thermal fluctuation of the system on the order of KBT level also help you to overcome the barrier and go to the global minimum energy state. If that happens, then the butterfly is terminated and you go to the W shape or the M shape. Basically, when you have the Ferro-Valleytricity, you are trapped in a local minimum of the free energy, while when you go to the other valley, you go to the global minimum. So through some analysis, you can roughly tell what is the orbital magnetization, what's the G factor correspond to the orbital magnetization, because KBT give you sort of an energy scale. And if you do that simple analysis, you can get orbital magnetization with G factor on the order of 20. which is 10 times bigger than the spin. It's actually not that surprising for a small bandgap material like this. Okay, so let's zoom out a little bit from the phenomena and think about what does this mean. Okay, so I was trying to tell you there is a Valley order, and the field that conjugate to the Ferro-Valley order is E dot B. So this compared with a more conventional ferroic orders we have been familiar with, ferromagnetic, ferroelectric, ferroelastic, and ferrotoroidicity. This is a new ferroic order where the valley, or which part of the Brownian zone does the electron occupy, is an order parameter. And the conjugate field is somewhat similar to the ferrotoroidicity, where it's E cross B, while what we have is E dot B, okay? No matter if it's a cross product or dot product, they both break time reversal symmetry, they break inversion symmetry, but they respect PT symmetry, okay? If you have K value, you first do time reversal and then do inversion symmetry, you're going to go back to the K value. And one way to think about, okay, so and of course, in this system, we also have the ferromagnetism, right? And that's orbital origin. So both the magnetism and the Ferro-Valleytricity are of orbital nature instead of having anything to do with spin. So we think this is, probably you can call it orbital multifluidicity. And one way to think about how they work or coexist is to think about the free energy like this. It's a product of some coefficient times valley polarization times electric field times B. And of course, here for 2D material, we only care about the electric field and magnetic field out of play. So these E and B are effectively scalar. If you only care about how it behaves in magnetic field, then you sort of look at this free energy as minus m dot B, where your m is effective orbital magnetization that depends on the valley polarization and the electric field you apply. But if you decide to look at this as valley as a order parameter, then the field conjugated with that in the free energy will be something like E dot B, right? And this is what we observe. So these two orders kind of coexist because it's dominated by the same terminal free energy as in a type 2 multifluidic. Remember, as we warm up the sample, the butterfly would eventually disappear at about 2 Kelvin. Well, if you trace the magnetic hysteresis at this different charge density, you see at low temperature, you get a big hysteresis loop. At, well, when you go to something like 2 Kelvin, the hysteresis loop is almost gone. So these two things kind of disappear at the same time. And another way of looking at this butterfly is that, okay, there are 4 states, right? Valley and orbital magnetization. Yes, please.
What about the spatial aspect of this? Gas states, magnetic domain.
Okay, so
you specifically talk about topological insulators. It's not homogeneous at all.
So
you had a magnetic material for that.
that's a very good question. Microscopically, we don't know if there are domains and how to distribute things, but basically, no matter you get the W shape or the butterfly shape, you align everything already. There's no additional jumps to even bigger. Okay. Right. So we think the whole thing kind of flip. Whole thing flips. I'm sorry. Okay, so I think here we're only talking about the bulk state contribution because we're at the doped sample, right? If we're in the if we're in somewhat a gap of topological insulator states, then the edge state will completely dominate the behavior. But here we are cutting through the Fermi, the band. Yes. So another way of looking at this butterfly is that, okay, you have 2 things. You have this valley and the magnetization. Okay, you got a total of 4 states. And with a small magnetic field applied, when you go through the butterfly, depending on the history of your scanning of electric field, you can actually control the valley and the orbital magnetization independently. You can keep, for example, if you just scan your electric field and you can keep the orbital magnetization with the same sign, but switch the valley, okay? Go from K to K prime valley. Or you can keep the valley to be the same and switch the sign of the orbital magnetization by purely scanning an electric field, okay? So we think this is quite interesting in the sense that you can just use the electric field without any current flowing in and out of the sample or changing the doping of the graphene. You can reach a simultaneous independent control of the valley and the orbital magnetization. Okay, so let's see. Okay, I have 10 minutes. So that's what we have observed in the doped pentalayer graphene, right? And we focus on the phenomena in the bubble. And the next thing I'm going to show you is what happens when you go along the electric field direction and keep the sample pretty much charge neutral. So you see shade, put the shades on this doped region and just focus now on the region that close to charge density equals 0. As you see, at the D equals 0, N equals 0, this is just a pristine pentalayer graphene, okay? You don't apply any voltage at all. According to the band structure calculation, you have large density states, so you'd expect a very good metal at this point, but instead you get a very insulating state, okay? At 100 millikelvin, it's like 10 megohm or even bigger in resistance. So this already tells you that correlation from this flat band has already gapped out the Fermi surface and give you a very insulating, correlated insulating state. And when you apply bigger and bigger displacement field, but stay at pretty much charge neutral, you see this correlated insulating state persists for a while before you get into some metallic or semi-metallic state. And then applying bigger electric field, you again get an insulating state, but we think this insulating state at a high displacement field probably correspond to just the inversion symmetric breaking under the band insulator picture. And when you apply a magnetic field of 2 Tesla, you see the same plot. Now you have more features to look at, okay? There are dips in RXX in the region where it corresponds to a displacement field that closes the insulating state, okay? You go from insulator to metal to insulator, and in the region of D corresponding to the metal, by applying field, you got additional features that give you dips in RXX, okay? So, yeah, so, these are some, temperature dependence of the resistance of these 2 insulating states. On the high displacement field side, we think it's band insulator, while in the middle, we think it's correlated insulator. And one way to differentiate them is as a function of temperature, you see the 2 band insulators have resistance changing in a way that can, at least at the high temperature side, can be fitted by an exponential dependence. That means you have a fixed band gap and you're just populating charges in there and you get smaller resistance. But if you look at the correlated insulating state, at the lowest temperature, it is like 10 times more resistive than the band insulator state. But as you warm up the sample, that resistance in the CI state decreases so fast, it quickly become more conducting than the other 2 states. And eventually at about 40 Kelvin, this insulating state, correlating insulating state now becomes several times more conducting than those band insulator state. So we think what's going on here is that the band gap itself is decreasing as you warm up. So you're doping charge into a shrinking band gap, and that gives you a resistance decrease that's faster than just a single particle band being populated by temperature. And if you warm up to even higher temperature, say at 40 Kelvin, although this insulating state at D equals 0 is already more conducting than the band insulators, but it is still more resistive than the neighboring state at intermediate displacement field. But if you keep warming it up to something like 100 Kelvin, you see this peak in the middle is completely gone, and you even get a small dip in here. So we think at this temperature, high enough temperature, you can probably completely abandon the correlation picture and just think of this as a large density of states metal, and that's very conducting. Okay, so now let me show you more data corresponding to the state at 2 Tesla. Okay, these are in the region of displacement field corresponding to the band closing or the metal state. Zooming in there, okay, this plot is 2 Kelvin to show you all the features. But if you want to know what these circles are in this region, you can decrease the magnetic field to 1 Tesla. As you can see at 1 Tesla, this is the gap of that metallic state, okay? And you have a dip here in RxX, and you have some blob features in the RxY channel. If you do a line cut through this dot in the middle at about 0.16 volt per nanometer displacement field, you find your RxX is a dip almost to zero, and your RxY is quantized at like h/5 squared. So this tells you there's some state that has a Chern number 5 in it. Another way to see the Chern number 5 or -5 is you stay at the same displacement field and you change the charge density and the magnetic field at the same time to perform the so-called Landau-Fan scan. And you get this state here that has a slope according to the Strada formula. It also has a Chern number of -5. Okay, so the bizarre thing is, you may think this is just an integer quantum Hall state, but if you look at this RxY and RxX map, you see these are other features corresponding to in the integer quantum Hall state, but they are so weak compared to the one that we are talking about. At the field of 1 Tesla, where this C equals -5 state just appear, it's already perfectly quantized. Okay, RxY is perfectly quantized, RxX is almost 0 once it shows up. Okay, well, all other states, these features are so weak at the same magnetic field, so we think this state of C equals -5 should be thought of as a Chern insulator state that's more robust than the integer quantum Hall. And of course, this state doesn't persist to 0 yet, so it's not a quantum anomalous Hall yet, but we have some thought about what is going on, and how to probably make it more stabilized at the even lower magnetic field. So clearly there's some competing state. When the magnetic field is too small, this C equals -5 is not the ground state to be chosen. Okay, and there has been some theoretical discussion of such kind of Fermi surface instability at charge neutral point when the band is flat. What kind of correlated gap you can open, and what is the spin and the valley distribution of the topmost and bottommost layer. And one state that was argued by some theorists is a so-called layer antiferromagnetic state, where spin has a spontaneous polarization over the 2 layers. We don't know at this moment if that's the case or not, but if we take that for real, maybe what's going on in our case is you start with a layer antiferromagnetic state. As you apply displacement field, you're shrinking the gap of the spin up species, and you're increasing the gap of the spin up species, and you're shrinking the gap of the spin down species. Sorry, this is a typo. This should be spin down. And maybe at some point, you close one of the gap and then reopen it. So the barrier curvature and the Chern number of that species got flipped upside down. Then you have 3 copies with the same Chern number. The other copy has the opposite Chern number. You add them up, you get the C equals -5 state. Well, at this moment, this is more or less phenomenological. We don't know if this is the right picture to think of, but this observation of C equals -5 manifests that you can have a topological state in a crystalline graphene without moire. So to summarize, I've shown you what we have been doing by doing spectroscopy and DC transport in exploring the correlation topology phenomenon in still the graphene multilayers. And we think it's just a beginning because there are many open questions that we would love to answer through further experiment. For example, I told you inside the bubble, there is regions that give you this very porous half metal state in a wing shape, right? But we don't know what the bubble itself means, okay? We don't know what the bubble itself is, why only part of the bubble shows anomalous Hall and the value polarization and the quantum oscillation. And that is one question to be answered. And of course, as you know, people have found superconductivity in trilayer rhombohedral graphene or even bilayer graphene. We think we have all the phase boundaries as being reported, so probably all what it takes to get superconductivity is just a lower electronic temperature. Right? And of course, the C equals -5 state is somewhat intriguing, considering there's no moire at all, and whether it's possible to stabilize it to 0 magnetic field and get quantum anomalous Hall. And how does all these phenomena depending on the layer number, right? I've been focusing on n equals 5, but what if you change a little bit to 6, to 4, 7? We don't know yet. Okay, so with this, I'd like to wrap my talk and thank you for your attention.
Okay, thank you very much. Jesse, could you tell people online that it's like this question?
Yes. So yeah, the audience online, please type in your question and then Naomi can read it, I guess.
Yeah, questions here?
So I see one question, and it's asking, are these bands actual entanglements via photonics? I'm sorry.
Are these bands existing photonic system? Is that what the question is?
It says, are these bands actual entanglements via photonics?
Okay, I'm not sure if I understand it, but it sounds like it's some photonics guy asking whether you can get such kind of flat band in photonic system. I don't know the exact answer, but I think that's an interesting question to think about.
Okay, and then you have another question. Can you please explain the non-metonics, and I might be pronouncing that wrong, butterfly, and is the hysteresis or hysteresis due to domain wall pinning, and what are the domains?
Okay, so this is a question that Bob was kind of asking. So our observation is that either choose the butterfly or the M shape. No matter which one it is, in terms of the amplitude of RxY, it is maximized already. There's no like steps in there to jump once and twice. So most likely this whole thing got pinged and then it flipped as a whole thing instead of gradually changing based on our observation.
Okay.
I had a question about with the Valleytronics back in germanium, people used to think about that. But with the trouble is that the system will flip from one valley to the other due to whatever reason.
Mm-hmm.
And you have a concept of why do the valleys stay put? If you put electrons in one valley, it stays there. Or is there something more complicated that's going on, or maybe they just don't tend to get kicked around?
So I think if you break the inversion symmetry and your bands get Barry curvature and orbital magnetism, you can probably think about the behavior just in the picture of magnetism, right? There's coupling. Yeah, there's but it seems that even if your state has zero magnetism, say Rxy equals 0, when you go along the butterfly, right, the state's in the middle, that tells you the system can stay in the same valley even if there's no magnetism associated with that. So that is interesting, and we don't know exactly whether there should be another energy we should consider or what. But in our picture now, no. Yes.
Presumably your help here relative to, as I understand, Valleytronics in the semiconductor business. Here you really have very large cooperativity because you're really opening up a gap between, it's like ferromagnetism in the sense that there's a strong exchange energy that wants all the electrons to be in the same valley.
Mm-hmm.
So kicking one out doesn't do much for you. You have to kick a very large number of them out, whereas, as I understood, what was thought of in Valleytronics and semiconductors, you don't have an energy gap to protect you.
Yeah, here, yeah. So I guess in that sense, here you have to flip everything at the same time.
This is just going back to the very beginning when you showed these plots, you pull them photoconductance.
Yes.
It was photocurrent or photo, I wasn't quite sure what was the measurement you're putting on a DC voltage and measuring the inductance as a function of the?
Yeah. So we can do both, right? We can just shine light on it and measure current that's generated without bias, or we can.
You do get, so there is a, but what you were showing was, what you were showing on the slide, I wasn't sure whether that was something that was in the presence of an applied bias or without a bias.
Typically, we can connect both part. We connect the photocurrent and the photo conduction, right? You are probably thinking about it. Okay, if you don't apply any bias voltage, what does that photocurrent mean? So the reality is you have a huge beam spot. In our case, like beam spot.
Yeah.
The beam spot is on the order of 1 millimeter, and have a tiny little sample there. And the sample could very likely have asymmetry between the source and drain, actually. So I have never seen any sample in 2D material that you shine light without bias and you don't get current. Usually you always get some current. But that could be due to the trivial reasons of asymmetry between electrode or photothermal electric effect, things like that. But for us, what matters is not the absolute amplitude of the signal, it's how the signal distributes as a function of photon energy. So in our case, I think we check both the photocurrent part and the photoconductivity part. And most of the time, they give you the same spectrum.
The proportion.
Yes.
Okay, one last question. Okay, well, I guess not. A lot of fascinating results. So thanks very much.
Okay, thank you.
Thank you.
Forgot to mention, I think this is the very last Sequum talk.
Yes.
And I couldn't thank Bob and the people involved in Sequum enough to appreciate your help. It's been a very enjoyable experience, and I hope we got something else to work together
Well, I hope
after
so.
Sequum.
Yeah.
Yeah.